Resistivity of metals increases on increasing the temperature. If the temperature change is not too large, the relation between the resistivity and the temperature for metallic substances can be described by the following empirical relation. Rho T is equal to rho 20 into 1 plus alpha into T minus 20. Here, rho T is the resistivity at T degrees Celsius temperature and rho 20 is the resistivity at 20 degrees Celsius temperature. Alpha is also called the temperature coefficient of resistivity. The following table gives the values of alpha for some materials. For aluminium, alpha is equal to 0.0039 per degree centigrade. For copper, alpha is equal to 0.00393 per degree centigrade. For silver, alpha is equal to 0.038 per degree centigrade. For tungsten, alpha is equal to 0.0045 per degree centigrade. For nichrome, alpha is equal to 0.0004 per degree centigrade. For manganese, which comprises of Cu, that is copper, 84%, Mn, that is manganese, 12%, and Ni, that is nickel, 4%. Alpha is equal to 0.000000 per degree centigrade. For carbon, alpha is equal to minus 0.0005 per degree centigrade. Note that the value of alpha for carbon is negative, which is not a metal. Returning to Ohm's law, V is equal to I into R. If the voltage V is applied to a conductor of length L and cross-section of the area A, the electric field strength is E is equal to V upon L. Therefore, V is equal to E into L. We have R is equal to rho into L upon A. Using equation, we get EL is equal to I into L upon A into rho. Therefore, E is equal to I into rho upon A. Now, remember that the current I is due to the drift velocity v of the electrons. The electrons moving with velocity v and passing through the cross-section of the conductor in 1 second will be contained in length L of the conductor. If the number of electrons is n, then this implies that the number of such electrons contained in the length L of the conductor is n into A into V. The total charge carried by these electrons is given by NaEV. This amount of charge passes across any cross-section of the conductor per unit time. Therefore, the current is I is equal to N into A into E into V. Using this result in the equation, E is equal to N into A into E into V into rho upon A. That is equal to N into E into V into rho. If the electric field in a conductor is E, then the force acting on an electron is E, and its acceleration is A is equal to E upon m, m being the mass of an electron. T as an average time spent by an electron between its two successive collisions with the ions, also called the relaxation time, then the velocity v acquired by it during this time interval is v is equal to a into t, that is E into E upon m into t, using the equation E is equal to n into E into rho into E upon m into t. Therefore, rho is equal to m upon n into E square into t. As the temperature of a conductor increases, the oscillations of ions increase both in their amplitude and speed. This results in the reduction of the relaxation time T between the successive collisions, resulting in the increase in resistivity. Figure shows how resistivity changes with the temperature for 1. A normal metal, 2. A material going into a superior conducting state, and 3. A semiconducting material. Note that at higher temperatures, the temperature dependence of resistivity is not linear.